Okay, I think we are live right now. So let's get started. All right. So last week we talked a little bit about traversal and how traversal works and how it's essentially the skeleton key of algorithms and how we can use it in programming competitions. But before I cover the next part of our journey to understanding traversal, I want to tell you a little bit about the divisional or the mock divisional contest that is taking place next Saturday, Saturday the 17th of October. If you want to register for that, please email Dr. Lijun Chang by Wednesday. He needs all of that, all the names of all of your 3 team members in order to, and your student emails and everything to register you for the competition. Okay, now that that's done, let's move on and let's cover some traversal. So, yeah, last week we talked a little bit about what traversal is and how we do it, and I want to kind of recall what we managed to code by the end of last week, which was our walk function, which looks a little bit like this. Let me write something down. Okay, so we had a function which is define walk GS, where G is a graph, which we talked about last week, and S is our source. And what we do is we essentially have 2 data structures. One is called P, which stores the previous or parent node of a given node or vertex. So essentially where it came from in the traversal. And we also have another data structure called Q, which in our case is a set. It could also be a double-ended queue, as we saw in breadth first search last week, or it could just be an ordinary list. So Q is a list of vertices we intend to visit. And what we did was we first added S to the queue. So this is how we do traversal. So first we add S to the queue, q.add S, and we set P S to be none because S is the source, so S did not come from any node. Now what? So how do we do it? So first we check if the queue is non-empty, which it isn't because we just added the source to the queue. And while there are still vertices to visit, we pop a vertex from the queue. So u equals q.pop. The ordering is based on which traversal algorithm you're using, but I'm just going to use any traversal. Like, we don't really care about the order in this case. We're just going to do any traversal that is fast enough, basically. So we take some vertex from the queue. Now we visit all of its neighbors. So we write for v in gu, where gu is the neighbors of u in the graph G, if v not in P. So if we haven't visited V, if we haven't visited V, and V is a neighbor of U, then we should add V to our queue. Q.add V. What that means is now we should visit V, and in the next iteration we will. And of course we will set P of V equals U, meaning that our vertex V came from our vertex U. Or in other words, U was the parent of V. right? So if we want to walk back in the order that we visited, what we will do is we'll simply look back in P and we'll check from the destination vertex we want to go to what was the ordering, and we'll just walk backwards. So we'll go to the parent and then the parent of the parent and so forth. So if we just want a list of all the nodes we visited, we can just write something like this. We can keep a list of keys like this, keys, and for k in P, keys, dot append k, and just return keys. So this code kind of essentially tells you what traversal is about. We add our source to the queue. We look through the source's neighbors. If we haven't visited them, we add them to the queue. And in the next iteration, we just pop another vertex from the queue and do the same thing again and again until the queue is empty. So until we get to a point where all of our neighbors have been visited and we can't explore anymore, and then our traversal is done. Now you might ask, what happens if the graph is not necessarily connected? And that's a very good question. So let me cover that. So the question is, what happens if the graph isn't connected? And I'm going to draw an example. So for example, A is connected to B by an undirected edge, meaning B is also connected to A. And we have also C being connected to D, but there are no connections in between B and C and A and D, or B and D and A and C. So these are kind of two components, these are what we call components of a graph that are connected, or connected components. Right? So A and B are connected, and they're one kind of little piece of our graph. And C and D are another connected component, and they're the second piece of our graph. So this graph, G, which we'll define in kind of code as like A being connected to B, comma, B being connected to A, C is connected to D, and D is connected to C. So this is how we would write that in Python, right? A is connected to B, B is connected to A, C is connected to D, D is connected to C. So this graph G has two connected components. I hope that's clear. So does our walk function work? So what happens if we run the walk function that we just coded on A? So we add A to our queue. A is the source. Then for all neighbors of A, we visit them and we add them to the queue. And we then visit the next element of our queue. So we will add B, we will visit B, and then we will stop. So the walk function only visits a connected component of the particular source node. So what do I mean by that? So if I started at D, let me do this so you can see the graph. If I started at D, it would visit D's connected component, which is C and D. Whereas if I started with B or A, we would visit this connected component and we wouldn't see this, because there's no way to get from A to C or D, or B to C or D. If we start here, we can never get there. We can't jump because there are no edges from which we can jump. So, in order to correct this, to visit every single part of the graph, we want to run that walk traversal function on both connected components. And there's an easy way to do this. The trick is you make a set of nodes that you have seen. So for example, when you go through the first connected component, you make a list, for example, that I have seen A and B. So when I look for a node or iterate over all nodes, when I iterate over all nodes to run our walk function over, if we've run it on A, we won't run it on B because we've already seen B in the first connected component of A. Does that make sense? So when we run our function, we'll run it on A, and because B is in the connected component of A, as in we can reach B from A, we'll kind of keep track of a list of vertices that we've already visited. So when we get to B, we won't run the walk function. Then when we see C, we'll know that we haven't seen it. It's not in a connected component of any of the nodes that we've seen, so we should run it. Okay, let's write out that logic in code. So what we will do is I'll write a function like this. Define components G. So it takes in a graph, and what I want it to do is spit out all of the connected components of that graph. Okay? So I'll make a list of components. So essentially for the graph above, I want it to spit out AB and then CD as the two particular components. All right, so comp is this. We make a set of nodes that we have seen, and for each node U in G, if we've seen it, if U in seen, we just continue, we don't do anything, and otherwise we make the component C equals walk GU. So otherwise we run the walk function, and then we just write comp dot append C. And what we've got is just a list of connected components, and we're just going to return comp. Return comp. And comp is storing all connected components, whereas C is storing just one connected component. One connected component. Okay, I've written enough, so what I'm going to do now is go to a problem where we can kind of see this idea in action. Alright, here we go. Here is our problem for this week. So let's have a read. First thing we should look at is the time limit. So we have 0.333 seconds. Okay, that's less than 1 second. Hopefully the input is fairly small. Yes, it is. H and W is less than or equal to 100. So it's not too bad. But let's look at the task. You have been contracted by a company which is mapping Pacific Islands. They have been taking photographs of islands from aircrafts to produce their maps. The photographs have been converted to grids showing where land is present and where there is water. You have been called on to help the map makers count the number of islands in their photos. The task is complicated by the fact that some of the islands have lakes and lagoons which show up as water in the photographs. Okay, for example, consider the photograph. It looks like this. X denotes land, dot denotes water. Okay, so this is all land over here. This seems like land. The photograph contains 4 islands, A, B, C, and D. Okay, makes sense. They have been designated A, B, C, D in the diagram below. Note that two land squares in the grid are considered adjacent if they share an edge horizontally or vertically, so not diagonally. Two land squares are part of the same island if they can be reached from one another via an adjacent sequence of land squares. In the event that an island contains a lake which contains an island, the two islands are counted as separate islands. Okay, yeah, so for example, if we do something like this, then the boundary, that's one island, and this over here is another island, the middle part. So what we want to do is to read a map and produce as output the number of islands contained in the map. So we've been learning a little bit about graphs so far. And the trick is here to map this problem into a graph problem. So let's figure out how to build the graph. And since we've been talking a little bit about connected components already, the solution is probably going to involve some connected components. So my question is, what is the hidden graph here? Let me put on my camera. Okay. So what is the hidden graph? Well, let's think about the map, okay? So we have a bunch of dots, and then we have some X's, like this maybe. Something like this, okay? So these are two islands. This is one, and this here is another island. So there are two islands in this picture. Okay, so what is the graph? We need to find the number of islands, okay? So we know that these x's are kind of connected to each other if they kind of share an edge, horizontally or vertically. So two land squares are adjacent, so they're part of the same island. So two land squares are part of the same land squares are part of the same island if they share a vertical or horizontal right? So if I have two squares, both are marked X, and they're horizontally adjacent or they are vertically adjacent, like this, then they are part of the same island. Now, what did I tell you about connected components earlier? We saw that a connected component, so two nodes, are part of the same connected component if there is a path from one vertex to the other. In other words, through the edges. Similarly, if two land squares are part of the same island, if they kind of share a vertical or horizontal edge, it means that this X and this X are also part of the same island because they're connected to this, which is connected to this. So if I can find a path connected by like horizontal or vertical edges from one X to another, we're in the same island. In the same way, with the connected components, if I have two nodes and I can find a path through the edges from one from one vertex to the other, then those two vertices are part of the same connected component. All right. So what does this mean? It means that there is a hidden graph here, right? The islands have some very, very analogous ideas with the connected components. So here's how we will define our graph. So if two nodes are marked X and horizontally or vertically adjacent, then they share an edge. Oh, sorry, I wouldn't say they share an edge. Then there is an edge between the nodes in the graph. Then there is an edge between the nodes in the graph. So what do I mean by this? Okay, let's kind of consider the islands as coordinates, and let's do the previous example. So I had something like this. Something like this, okay, where we had two islands here. Sorry, that goes there. So we had two islands that looked like this, and we had another island that looked like that, okay? So let's say this is coordinate, say 1, 0, 2, 0, 3, 0, okay? 3, 0, and this is coordinate 4, 0. They're both marked with an X, and they're horizontally adjacent. So in our graph, we have two nodes. One is like 3, 0, one is like 4, 0, and they are connected together. Does that make sense? So they're now connected in the graph. In a similar manner, this X here would be 3, 1. So 3 across, 1 down, and it would be connected to 3, 0. 3, 1, because it is vertically adjacent from 3, 0. So it is part of the same connected component. On the other hand, this coordinate, which is 1, 4, 1, 4, would not be part of any other connected component in the graph. It kind of makes up its own connected component and its own island because it is not adjacent to anything else, any other x's. So the idea is that we have to build this graph where these two coordinates, they share an edge if they're both x and they are vertically or horizontally adjacent, and then find the number of connected components in this graph. So let's code that up. Let's code it up. Let's get started. All right, so the first thing we're going to do is we're going to code up our walk and our components from last week, which is our traversal functions. So handy, I'm hoping this all works out. Let me just check my, yeah, good. My stream is working. Handy traversal to get the number of connected components. So we have two functions. Define walk gs. P is a dictionary to store the previous or parent node of a node. Q is a set. P of s is none. We add the source to the queue, and now we do our magic traversal, which is, while the queue is non-empty, we take a vertex from the queue, And for each v in G of u, if v is not in P, so in other words, if we haven't seen it before, then we add it to the queue, and we set PV equals U because we want to make sure we store the parent of V, which is U. If we want, in case we ever want to walk back. Okay, and then we'll do something like this: keys for K and P, keys dot append K. And we'll return the keys. So this just gives us everything in P, which is just all the vertices in a given connected component. Now we'll implement the components function, which is define components G. We define a list comp to store our components. We make a set for all of the C nodes so we don't run the walk function too many times. For each U in G, if U is in scene, continue, otherwise C is walk GU, and then we update scene.update C and comp.append C. Return comp. Okay, so that gives us our connected components. But now we have to actually have to solve the question. How are we going to do it? So the first thing we need to do is we need to read the input file. What does the input file actually look like? So let me go to that and let's find out. So this is what an input file looks like. We have 3, 5, meaning that we have a height and a width, H and W. We can always check the input specifications. We can check the input specifications here. Let's take a look. I think H and W are the height and width. Yes, the height and width of the map. So for example, 3, 5, what does that mean? It means that the height is 3 and we have 5 things to read and 3 lines to read. Cool? So we have to read in all of these X's and dots, and we have to make sense of it. So the first thing we have to do is actually build the graph from the input file. So let's read that. So let's go back to our Python code. First, we should open our file, which is cartin.txt. For reading, we should read our HW. So HW is map of f.readLine. Okay. Okay, now what we're going to do is we'll define a grid. So we'll define a grid to store the entire map of the island. So we'll make a list. We'll call it grid, and for each line in our file, we're going to systematically append everything to the grid. This is not the most efficient way to do it, but it's good enough. So the point is I'm taking some line of input, I'm removing all the extraneous stuff from it, and then I'm appending this line as a string, character by character, into some list L, and then appending that list L, that 1D list L, into a grid to create a 2D array. This is kind of a handy trick. There's probably a more efficient way to do this, but this is like a pretty handy way of just constructing a 2D array very fast. Okay, now what do we need to do? We have to keep going. Well, we have to first define our graph. So let's make graph G, and it's an empty dictionary because it currently has no nodes. Fair enough. It has no nodes. So how do we give it nodes? Essentially what we said was that if we have two nodes, they're both adjacent horizontally and vertically, and they're both x, then we should add them. But we have to watch out for all of these kind of nasty exceptions when we go off the grid, when we go off the map, if we go upwards, if we go downwards. And there are kind of all kinds of nasty things we've got to just make sure we don't mess up. So what we're going to do is we first have to loop through everything in the grid. So for I in range len grid, for j in range len grid I, meaning h and w in this case, let's write square equals grid ij. So what this is saying is that the ijth element of that grid is what we're going to look at. Okay? So if the square is an x, if we're looking at an x, we need to check for all neighbors, right? So if the square is an x, we create something for that ij. Ij is a set. So what that's saying is that we create a set of neighbors to store the neighbors of this ijth element. And since we only look through that element once, since we only look through that square once, then everything is fine. So we won't have problems with declaring it again because we only see each square once. Okay. So now we're going to do a try catch in here. So if the square is x, we'll try all of the neighbors. So if grid I minus 1j is an x, and I minus 1 is bigger than 0. In other words, and we're at a point where the left square from here is not off the grid, then we should add it. So g of this ij, so g of our square, in this particular case, well not the square, the actual coordinate of the square, right? Because square is grid of ij, so this is just the coordinate of the square. We'll add the neighbor I minus 1j. And I hope you see where this is going. Of course, if there is an exception, we don't care, so we'll just write pass. I hope you can see where this is going. We're going to do this for all four of the neighbors of this graph. So let's do it for the second neighbor. So if grid I plus 1j is an x, so in other words, if our right neighbor is also an x and our square is an x, so there are two nodes that are both x's and they're adjacent from the right, and we don't go off the grid. So how do we express the fact that we're not going to go off the grid here? I'm not particularly sure how we do that. Oh, here's an idea. So we might write I plus 1 is less than the length of our grid, right? Which means we haven't gone too far. We haven't gone more than W, right? So we never have to check a right cell if we are at the rightmost cell. That's the essence of the idea. Then we should do this. G of ij dot add I plus 1j. Okay? And of course, we will accept our exceptions. I mean, I'm coding this fairly fast, so Obviously, this might not be the best way to code this up, but it's one way to code it up. Again, we'll do the third neighbor. If grid ij, if grid I, we'll do j minus 1, because now we're going vertically. We're going vertically upwards, and we're checking that. If that's also an x, and j minus 1 is bigger than 0, similar to the I minus 1 is bigger than 0 for our first neighbor to the left, then what we're going to do is g of this ij's neighbor is going to be ij minus 1. Okay, and finally, we will do the last neighbor, which is the ij plus 1th neighbor. In other words, downwards, not upwards, downwards, because we just did upwards. So if grid I j plus 1 is x and j plus 1 is less than the length of the grid I, that looks good. Yeah, it's grid I, not grid, because we're looking, because the grids may not be the same length, you see? And if it's less than the length of the grid, then we have to add, so g of this ijth element, and we add it to the, and we add the ij plus 1th edge, the ij plus 1th node to the neighbor of the ijth. Cool. And accept the exception. Okay, so what we've done here is we've constructed the entire graph. For each neighbor, if we have two neighbors with an x that are horizontally or vertically adjacent from each other in the map, they will now be neighbors in the graph. So all we have to do, now that we've spent all of this time implementing this components function, implementing the walk function, and defining the graph, we're almost done. Because now what do? We simply do this. We write comp equals components g, and that gives us all of the connected components of this graph. And our answer, what we need to output is the length of comp. The length of comp. Okay, so what we got here is all the connected components, and this is the number of connected components of G, which is the number of islands. Okay, now all we have to do is just output the answer to the output file. So output file is open. In this case, it's cartout.txt. Of course, I hope everyone remembers how to read and write to text files. Output file.write. And we'll just write the string value of our answer and close our input and output files. And that should be it for this question. So, it was a lot of code. We had to write a lot. But if you notice, a lot of our code was pre-written. This components and walk code is something that we should already know and something that we should already have handy and written up. What these two things do is, first of all, traverse through a single connected component. That's what we covered last week. Not just defining graphs and understanding how graphs work, but also being able to go through one connected component of a graph. We also kind of covered it and revised it today. And being able to find all of the connected components of a graph. So organize the graph into the parts that are connected and the parts that are not. And it turns out all it is just an application of the walk function a number of times. And we just need to add things to a list. You also see how valuable things like sets and dictionaries are now, right? We're using them liberally in all of our traversal because they're useful. Because if we've seen an element, we don't ever want to see it again. Make sense? That's why we use sets, because they provide that O1 membership check, and we don't have to actually go through all of the elements to check if we've seen something. That's why sets are so useful. They kind of, sets and dictionaries form the backbone of not just defining a graph, but also graph traversal itself. Then we built the graph. So this was, I think, the harder part, trying to make sure that what we were able to do was to show that if we had two nodes that were horizontally and vertically adjacent, and they were both x, they had an edge. They had an edge between the two nodes in the graph. And as a result of that, we had the kind of idea that if you have two x's that are kind of connected by some path, or by some chain of x's that goes horizontally and vertically, then they are part of the same island, so they are part of the same connected component in the graph. So we mapped a concept about, maps and geography/cartography into a concept from graph theory, and we used the graph concept of connected components and traversal to be able to solve the problem and output the answer, which happened to be exactly the same as the answer to our map problem. So that's how you go about solving the problem. And finally, we simply outputted the number of connected components that we needed, and after that, it was very, very simple. We simply got the length of the connected components, and that happened to be our answer. So what we want to do is, let me at least try and illustrate to you why this works on the test cases, or what our algorithm is just doing in case we didn't follow along. Okay, so let's look at this case. What we're going to do is we'll go through the coordinate 1, 0, which is a dot, 2, 0, which is a dot, 3, 0, which is a dot, and then 4, 0. Okay, 4, 0 is an x. It's the first x on the right in the first row. So what that will do now is we'll run the walk function on this particular node. And what that will do is once we have the entire graph done, well, first we have to build the graph, of course, but I'll cover that a little bit later. We build the graph and then we run through this. So it'll say, okay, 3, 0, what are its neighbors? Its neighbors are 4, 0, the x immediately to the right of it. And then the neighbors of that node is the x that is immediately down from that node. From 4, 0, it'll be 4, 1. And then 4, 2, there's another x downwards. And there's an x to the left, and so forth. Because we have all of those neighbors pre-built into the graph, we will be easily able to traverse them. We will add these x's to the queue, well, not the x's themselves, but the coordinates. And then, once we have those x's in the queue, or the coordinates in the queue, we will simply find the neighbors of those coordinates because we've already put them into the graph, and the traversal will work fine. Similarly, we will simply we will also find the number of connected components. We will also find the connected component on the left, which is, I think it is 1, 2, and 1, 3. Yeah, those two x's down the bottom. Those two will come as part of their own connected component because we will run the walk function from one of those nodes. Probably it'll be 1, 3 in this case, right? So we will just check for all of the nodes, all of the coordinates, and because they have their x's and they haven't been seen before, then we'll be totally fine, and we'll run the function, we'll get the connected component, and that'll all be defined, and we'll get our answer. I think that concludes what I wanted to do this week. There's another problem in the notes that I did kind of want to cover, but I think we'll look at it a little bit next week instead. It's again a lot about connected components, and it very easily follows from what we've been doing this week, but I'll save it for next week. All right, thanks everyone. I hope that was informative and interesting. And now you kind of know about not just traversal, but how to use traversal for a very important application, finding connected components in graphs, parts of the graphs that are connected, walking through those connected components, which is very useful in case you have to do any sort of processing on them, like for example, finding the number of islands in a map, and being able to build a graph from a bunch of information and kind of discover the hidden graph that we didn't think was there, but then we were able to see it when we saw the kind of connection between ideas about connected components and graphs and ideas about the maps and the islands. So I hope that was interesting, and I'll see you next week. Reminder about the divisional contest. It is on Saturday. Sorry, the regional contest. It's a mock regional contest. It's on Saturday. It's preparation for a contest that is on January the 23rd. I think I will confirm that. So make sure to email Dr. Legion Chang if you want to join. All right, thanks everybody. I will see you next week.